So let's get started. The first speaker is Aaron Bell. Aaron is an experimental petrologist interested in understanding processes that drive the development of magmatic redox diversity in terrestrial basalts, asteroidal basalts, and other planetary materials. He's a research scientist at the University of Colorado Boulder. Aaron, go ahead.
I appreciate the invite, everyone. So first, I want to start out with a little bit of an outline about what my talk's going to be about. And so to start out the talk, I want to give you a brief introduction into oxidation state and the oxidation state of igneous materials in particular in sort of a planetary context. Essentially, why is this important? Why should we be interested in measuring these things? And then I want to give you a little bit of background about sort of some what I call classical methods, not because they're from antiquity, but they're an older way to approach this problem of calculating FO2, as well as some of their shortcomings. And so I think this feeds nicely into the development of synchrotron-based techniques where we use polyvalent cations in silicate liquids. And so then I'll introduce the concept of using polyvalent cations in magmas as an oxybarometer, or a way that we can quantify FO2. And then finally, I want to basically talk a little bit about chromium valence measurements in particular. That's one thing that I've spent a lot of time on in the last several years. So I'm going to focus primarily on chromium in this talk. I know Tony earlier touched on vanadium. I had some vanadium slides in the talk that I took out. I think we're just going to stick to chromium. And then finally, I want to show you some applications, and I'll show you some real data and some places where this sort of approach to using cation valence in minerals as an oxybarometer has been applied to real rocks, real petrologic systems. So anyway, just to get started, for the non-petrologists in the crowd, I'm sure a lot of the igneous petrologists in the crowd probably know this already, but sort of I want to pose this question, you know, in a bigger sense. What's so important about understanding oxidation state anyway? And so from the planetary perspective, there's a number of reasons that this is important. So most importantly, understanding magmatic oxidation state feeds into our understanding of planetary differentiation, in particular, the formation of planetary cores. And so, for example, oxidation state directly, or the FO2 of the planetary system differentiating directly impacts the mass of the core that actually forms in the planetary body, as well as its composition. And the composition of planetary cores depend on FO2. So the partitioning of light elements like silicon is, of course, FO2 dependent. And the highly siderophile element composition of the core, as well as the composition of the residual mantle material that gets left behind, are all impacted by oxidation state. Another important application of understanding oxidation state is in the partial melting of asteroidal bodies. So in the petrology of small asteroidal sized bodies, we know that the silica activity of partial melts that are produced when these asteroidal bodies, for example, this is a picture of Thor Vesta, or a cartoon rendering of Thor Vesta and its small core. And so we know that the silica activity of partial melts, or the magma oceans that get produced on small bodies, directly depends on FO2. And so this brings something to mind, the angrite versus HED suite dichotomy. So if you differentiate asteroidal bodies under reducing conditions, you get things that look like Vesta, or Vesta here. These are are tholeiitic type liquids versus angrites. So angrites are this exotic basaltic achondrite. And so we have a few samples of meteorites of angrites. So angrites are what we would call critically silica undersaturated. They're very different compositionally than meteorites that we get from Thor Vesta. And so we know that this has been hypothesized to basically be a function of the oxidation state of iron in the system during differentiation. Another important aspect of understanding oxidation state is understanding magma ocean outgassing. And so the development of early planetary atmospheres is impacted by the oxidation state of planetary scale magma oceans that then outgas to form early atmospheres. And so the oxidation state of that magma ocean feeds directly into the speciation of the gases that form early planetary atmospheres. Another interesting aspect of this problem is that the geodynamic cycling of redox sensitive elements between geochemical reservoirs. So we know lots of planetary materials. There's a range of oxidation states among planetary materials, but having planets with redox diversity in a single system, like on Earth, may be fairly rare. So for example, we know on Earth we have plate tectonics, and we cycle redox sensitive elements between crustal reservoirs and deep Earth reservoirs. And so this is one way we contribute to the generation a diversity of oxidation state in terrestrial magmas. So on planets like the Moon and Mars, that's typically not so much the case. There's no tectonics on the Moon, of course, and so we don't get this redox cycling. And so lunar magmas basically have a very limited range of oxidation states. And so this geodynamic cycling, one fingerprint of plate tectonics might be the existence of redox diversity among basaltic magmas. And then finally, I'll just leave off with this last quick point. If we're interested in hydrous magmas, basically hydrous magmas, subduction zone magmatism, and Earth all require oxidized conditions. Lots of planets are quite reduced relative to Earth, and the water fugacity in those planetary interiors is low because of that. So they have a high hydrogen fugacity, low water fugacity. And so this basically precludes the existence or precludes the production of hydrous magmas. And so this term oxygen fugacity, I'm going to refer to as FO2 frequently. And basically it's a parameter that numerically defines oxidation state in petrologic and mineralogic systems. It's related to the chemical potential of oxygen in the system. And a good way to think of it is basically it's an effective thermodynamic partial pressure of oxygen in the system. Anyway, so a little bit about how we do this business in the first place. And so the classical approach to evaluating the FO2 of a volcanic rock or a magmatic rock of some sort would be to use mineral equilibria. And so typically the idea here is the coexistence of certain minerals basically can be used to define the oxidation state of the system. And here I'll give you a quick little example from an angritic meteorite. So this is one of these weird exotic critically silica undersaturated basalts. They're about 4.5 billion years old. This is a picture of Durbani. It's an angrite that fell in Argentina. And so basically we can assess the oxidation state of lots of materials. And in particular, this was developed for terrestrial basalts by using mineral equilibria. And so one example of this is we can use the composition of coexisting olivine with that of coexisting spinel, or the magnetite component of the spinel, and we can manipulate this reaction, and we can use it to basically calculate the oxidation state at which those two minerals coexisted. And so we can measure the composition of olivine in thin sections with the electron microprobe, and we can measure the composition of spinel with the electron microprobe as well. And then we can use those compositions, and we can do a little thermodynamic wizardry, and we can come up with FO2, an FO2 estimate. And so for angrites, basically the late stage angritic liquids had olivine coexisting with some ferric iron bearing ovospinel, and we can use this equilibrium, and we can calculate the FO2 of angrites. So this is sort of a classical approach, but this approach has some shortcomings and notably applied towards planetary systems. And so the most sort of notable of these shortcomings is that most planetary basalts or planetary materials that aren't terrestrial have very low ferric iron contents. So often there are very few spinels that have enough ferric iron that can be easily measured by charge balance with electron microprobe data or even with XANES. And so this is an issue. So if you have ferric iron poor materials, you often don't have the phase assemblages required to do this sort of thing. And the other problem is often, so in the case of the angrites here, this sort of little phase diagram I have, the olivine and the ovospinel that were used to calculate FO2 for angrites, these were very late in the liquid line of descent. So these phases crystallized in the very late stages of crystallization. And so this sort of phase equilibria analysis only provides information about the late stage evolution or the late stage oxidation state of that magma system. And so it doesn't necessarily tell us anything about the more primitive parental liquids from which the angrites were derived. And so this sort of is a big issue. And so one way in which we can sort of get around this problem, and you saw this diagram earlier that Tony showed, is we can use redox sensitive polyvalent elements in silicate melts. And so we know there's a whole range of transition metals that all exhibit polyvalent behavior when they're dissolved in silicate liquids. And basically, we can use the changing of valence as a function of FO2 of these polyvalent elements as a way in which we can retrieve redox information about magmas. And so the important point here is all of these sort of redox couples that I've shown here, chromium, vanadium, iron, europium, and even titanium, the valence changes for cations dissolved in silicate melts, unlike what you might be familiar with in mineral buffers. They don't occur at discrete FO2 values, rather they occur continuously over a range of FO2 values. So for example, this IW This stands for the iron wustite buffer. And so this is the mineralogical reaction where you transform metallic iron into wustite, which is FeO. And so this happens, of course, at a single discrete FO2. But the transformation of, for example, of chromium 2 plus to chromium 3 plus in silicate melts happens over a wide range of FO2. And so the basic idea here is pretty simple in that if we can measure, for example, the chromium valence ratio in a silicate melt, we can actually retrieve the FO2, provided we know something about the temperature, pressure, and temperature pressure conditions, as well as the melt composition. And so here's just an example of some old chromium valence data. These actually weren't done at a synchrotron facility. This was an old-fashioned way you could measure chromium valence using chromite solubility measurements from some experiments. And so essentially what you're seeing here is a plot of the chromium 2 plus to total chromium content of these basaltic melts from these experiments. And you can see that essentially as FO2 increases, or as the oxidation state increases down here on the x-axis, the chromium 2 plus content of the melt decreases smoothly as sort of a sigmoidal function of FO2. And so this is sort of the basis that underpins the idea that you can use polyvalent cations as redox or as oxybarometers. And so, for example, in this case, the chromium 2 plus to chromium 3 plus transition occurs over about 8 log units in FO2 space. This is a fairly wide transition. So essentially, you don't transition all the way to chromium 2 plus until somewhere up here. And this would be a melt with exclusively chromium 3 plus, or 2 plus down here and 3 plus down here. So there are some issues with this sort of approach as well. So this is typically used. So iron is much more common in terrestrial systems. So Mary Jo Browns, who's speaking after me, will talk, I think, about iron valence and how that's used as a proxy, a redox proxy for terrestrial silicate magmas. Anyway, so one of the issues with things like chromium is that direct measurements of chromium valence aren't really possible in iron 3 plus bearing glasses. And so there's essentially an intervalence, an electron exchange reaction that occurs in silicate liquids that essentially erases memory of chromium 2 plus that was present in the liquid. And so this reaction occurs when you quench silicate liquids to glass. And so this leaves this sort of approach wanting. And so, like I said, these measurements were inferred from chromite solubility. These aren't spectroscopic measurements. And so this is an issue. And so this means we have to sort of turn somewhere else to look for a more useful proxy that uses chromium valence as an oxybarometer. And so finally, I'll also say is quenched melts, quenched glasses and melt inclusions are quite rare in planetary materials. Even this is true to some degree on Earth. So it's very rare that you actually have quenched glass anyway. And even if we were, it wouldn't be particularly useful with respect to chromium, in that basically, like, quenched glasses don't preserve their chromium 2 plus heritage. And the other thing to note is most planetary magmas are actually much more reduced than terrestrial magmas. And so the ferric iron content of most planetary magmas is quite low and difficult to measure with XANES or synchrotron-based techniques. And so this leaves us sort of in want of a way to get around this problem. And so the way in which, one way in which you can get around this problem is to actually use silicate minerals or magmatic minerals as a proxy for chromium valence in their parental liquids. And so this is just a quick plot that's basically showing you the partition coefficient of chromium between olivine and liquid as a function of FO2. And you can see there's no slope here. This is a good thing. It basically means that olivine accommodates chromium 2 plus and chromium 3 plus in about equal measure. So if you were to write a KD expression for that, the KD for olivine and liquid for chromium is about 1. And so this has been borne out by numerous experimental studies. And so what this basically means is, although chromium 2 plus 3 plus ratios aren't preserved in quenched silicate liquids, they are preserved in olivine phenocrysts. And this is very convenient for petrologists, mainly because olivine is often the first phase on the to appear on the liquidus of primitive basaltic melts. And so olivine is pretty ubiquitous in these primitive basaltic melts that we're sort of interested in measuring the oxidation state of. So here's just a little bit of insight. So chromium 3 plus, actually, you might be wondering how chromium 3 plus goes into olivine. So it's actually a vacancy-based substitution. So you put in 2 chromium 3 plus a vacancy. So you leave one M2 site or one M1 site vacant in the structure, and you can put in 2 chromium 3 plus. And so that's how you accommodate trigonal chromium. So chromium 3 plus is about the right size. It's very similar in size to iron. And it also has some crystal field stabilization energy associated with its substitution into the olivine lattice. So basically it wants to be there. And so that's good news. And that we can basically, instead of using quenched melts, we can just look at chromium valence and olivine as a proxy. So anyway, just to prove to you that this works, here's a little bit of experimental data that I generated. And so this is experimental data over here. It was generated from an experiment in which we grew olivine phenocrysts from a basaltic liquid. And here's a backscatter image of that. So these are these little experimental olivine phenocrysts that we've grown. And then this sort of intermediate gray phase here is quenched glass. And so what we've done in this case, we've done experiments basically that were very low in ferric iron. And so what we've done is we've actually measured the chromium valence ratio in coexisting liquid and glass. And so over here, I have chromium 2 plus the total chrome plotted as a function of experimental FO2. And you can see that, so the green dots here, these are chromium valence ratios measured in olivine. And so the blue dots are their coexisting liquids. And so you can see that there's actually a really good match between those two, and they all fall nicely on this sigmoidal curve that was predicted for these liquids. So essentially, this data demonstrates that chromium valence in olivine does in fact mirror that of its parental liquid. So this is just sort of a way to prove that. This is just a picture of a quenched experimental glass that was actually analyzed. This is probably this experiment here. So this has little olivine crystals in it. And so you notice the experimental data only goes to the IW buffer. And so essentially beyond this is where the melts begin to have ferric iron. And so essentially if we were to measure chromium valence in the melt with those FO2s, we wouldn't see anything other than chromium 3 plus, as all the chromium 2 plus is basically destroyed on quench. Anyway, so how is it that we go about measuring chromium valence? And I'll just briefly go over this. So everyone's shown sort of a lot of people have already shown slides like this. And so this is just a little schematic of the beamline, 13 IDE at GSE cars at the advanced photon source. This is where all of the data I'm going to show today came from. And so we can measure chromium valence using X-ray absorption near its structure spectroscopy. And so these sorts of spectroscopic measurements essentially allow us to measure the binding energies associated with various bound state electron transition between empty orbitals, or between full and empty orbitals. So essentially this provides information on both cation coordination, geometry, and symmetry, as well as information on the oxidation state. You can also derive crystal field splitting energies from these sorts of measurements. So anyway, this is what a chromium K-edge XANES spectra actually looks like. So over here, we've plotted X-ray absorbance as a function of incident beam energy. And so to make these measurements, essentially we take a focused beam of several microns and we modulate the incident energy of that beam as it's illuminating the sample. And then we measure via fluorescence the absorbance the absorbance is a function of energy. And so in this sort of diagram, what you can see, and so this is a XANES spectra that was acquired for a chromium 2 plus standard glass. This came from Hansen and Jones, 1998. This is sort of a common standard material used for chromium. And so there's a couple of important features here. Number one, you can see that the energy of the white line is shifted to slightly lower energies for chromium 2 plus. And you can see that the energy of the main edge crest here, the white line, is shifted by about 5.5 eV. So the energy of the main edge crest shifts, but also there's this other important transition. And so this sort of hump on the side of bump on the side of the spectra has actually been attributed to the 1s 4s electron transition. And so this is an important spectral feature for chromium in that basically this transition is allowed for divalent chromium. So formally this transition, this is a 1s 4s transition, this would be symmetry forbidden. And so essentially this is not a transition that would be normally allowed. However, and so if you had chromium 2 plus in regular octahedral coordination, you wouldn't see this. But it turns out chromium 2 plus that's present in melts and olivine, actually it adopts an interesting range of coordination states. So they range from square planar all the way to highly, highly distorted octahedral coordination states. And so essentially anytime you have chromium 2 plus, it never adopts regular octahedral coordination like trivalent chromium does. And so this feature on the edge of the chromium, or on the main edge, this sort of 1s 4s transition, is important in that it's basically diagnostic of the presence of chromium 2 plus. And so I'll show you the next slide here. This is actually a slide that shows the results from a few experiments that I've done. And so you can clearly see these experiments were done at constant FO2 over a range of temperatures. And so you can clearly see that the 1s 4s transition feature here, diagnostic of chromium 2 plus, its intensity is a function of chromium 2+ content. And so we can basically quantify the chromium 2+ content of any given glass or olivine based on the intensity of this feature. And so typically we would look at this in just normalized absorbance versus energy. We might look at it in normalized, or the derivative of normalized absorbance versus energy. And so I'll show you a plot like that. And the basic idea here is pretty simple. The intensity of this feature, the integrated area under here, basically scales with the chromium 2+ to total chromium ratio. So this is for the most part true, although there are a few complications that are probably worth mentioning here. And so the intensity of this feature can also be impacted by changes in coordination symmetry among series of glasses. So for example, if we were to look at a titanium bearing glass versus a glass that had no titanium in it, we would see an impact. Basically the intensity of this feature would change slightly, even if they were performed with the same FO2 and had the exact same chromium 2+ to total chromium ratios. And that's basically a function of the bulk composition of the liquid has some impact on the local coordination symmetry of chromium, and that impacts this as well. So that's something to keep in mind. Anyway, so that's enough about liquids. We'll talk more about olivine. So we can make these similar sort of measurements in olivine, but with olivine, there's an additional complication in that essentially, whenever you do synchrotron micro-XANES measurements, you're using a beam that's linearly polarized. And so anyone who's ever done any IR spectroscopy with polarized light minerals is familiar with this sort of problem. And so the basic idea here is that when you use polarized light, there's actually a directional dependence of the absorbance of certain features. And so here, this is a plot of the derivative of the normalized absorbance. And here's our friend, the 1s4s absorption feature right here. And so this is a little bit different of a plot just because we're looking at derivative versus energy. And so essentially what I'm trying to illustrate here is that the intensity of this feature is not only in olivine a function of the chromium 2 to total chromium ratio, it's also a function of the crystallographic orientation of that olivine relative to the polarization direction of the beam. So I have this little cartoon here. And so essentially you can see this olivine's been rotated 45 degrees here and 90 degrees here. And so the crystallographic axes of this olivine, when they were rotated on the stage at the beamline, essentially changed relative to the polarization direction of the beam. And you can see that manifested in the intensity of this absorption feature. And this olivine basically has a constant, this is a single olivine crystal from a redox controlled experiment. It was grown for this very purpose to evaluate this. And so essentially this has a constant chromium 2+ to 3+ ratio, or chromium 2+ to total chromium ratio. And so this is an issue. And so this is also, for example, an issue if you're interested in iron valence in pyroxenes and other materials like that. So anyway, this is something to be aware of. There are ways to get around this. So if we know the crystallographic orientation of the olivine relative to the polarization direction of the beam, we can actually overcome this. And so we can define these angles like this. So we can actually make electron backscatter diffraction measurements of phenocrysts like this. This is actually the stereographic projection of the axes of this particular olivine. And so this little PD represents the polarization direction of the beam. And so we can actually define these angles. And so we can overcome this problem. And so this is—
Aaron, you need to finish up in the next minute or so.
Oh, okay, sorry. Anyway, so I'm going to show you a little bit of data. So this is some data from an olivine from McCarty's flow in the Zuni-Bandera volcanic field. And this shows some XANES data, chromium 2+ to total chromium ratios as a function of temperature. And here I plotted on here isopleths that show basically these are constant lines of constant FO2. And so you can see where the data plots. And so essentially this particular olivine was grown at about delta FMQ plus 0.25. Anyway, so I'll go ahead and finish up with that. And I'd be happy to take any questions that you guys have.
All right, thanks a lot. We have time for a quick question. I would point out that Joanne has put a number of pieces of information in the chat, so please check those out about surveys and the roundtable and other information. All right, well, I think we should move on. Please put any comments or questions in the chat for Aaron.